So in this video, we're going to work on some SAT problems that deal with growth and decay, and they are word problems. And the discussion we're about to have of this equation on the next screen should hopefully set you up for success on similar problems on your SAT. So this equation here, n is going to be the amount of the quantity that we're considering at any time. Maybe that amount is a population, maybe that amount is a number of coupons. One of the examples that we're going to do in a few minutes is going to involve a certain number of coupons. N is the amount of the quantity being measured. The way you're going to determine the amount of the quantity being measured is you're going to take the initial amount of that quantity. So N0 is the initial quantity, the initial population, the initial amount of coupons that the business distributed. We're going to multiply that by a set of parentheses that's raised to the t power. T is going to be the number of time frames. Might be years, might be days, might be hours. Kind of have to adjust it from situation to situation based on how things are phrased, but we'll definitely talk about some of those adjustments in some of our examples. So T is the number of time frames that have gone by, a certain number of years, certain number of months, certain number of days. What we're going to do is we're going to have to acknowledge what the growth rate or the decay rate is. So if the growth rate is 50%, we would represent that growth rate as a decimal. 50% divided by 100 would give us 0.5, and we would take 1 plus 0.5 in this set of parentheses. So it would end up being 1.5 raised to the t power. If it was a population that was decaying by 50% every year, we would subtract off 0.5. So you do have to be willing to adjust the sign of this, addition for growth and subtraction for decay. Let's go ahead and get into our examples here. So the first one says the equation E of t gives the estimated number of employees at a restaurant. T is the number of years since the restaurant opened. So in this case, t is being measured in years. Which of the following is the best interpretation of the number 5 within this context? There's not even really much work to do. If you have some familiarity with the equation that we just discussed a little bit about, this problem's really pretty straightforward. The 5 is out in front of the set of parentheses. We said a minute ago that out in front of that set of parentheses, you're going to have the initial quantity being measured. This function represents the number of employees at the restaurant. 5 must have been the initial number of employees at the restaurant. So if you read down through those options, option A seems like it's pretty good. The estimated number of employees when the restaurant opened, I think that sounds good. Let's just read through everything else, make sure nothing else seems any better. Don't think that it does. Really, the only one that makes any sense is option A. So this one says the population of Greenville is increasing by 7%, or it did increase by 7% from 2015 to 2016. The 2016 population is K times the 2015 population. What is the value of K? Now, I do have to adjust a few things here. Time is being measured in years, I believe, because 2015 to 2016, that is a 1-year jump. So from 2015 to 2016, I know my elapsed time is 1 year. My 2015 population, they don't tell me that, so I'm just going to represent it as N0. And check out what happens if I start plugging into this equation. The population in 2016 is going to equal whatever the 2015 population was times 1. It's growing, right? It was an increase in the population by 7%. So 1 plus 7% as a decimal would be 0.07. And then I'm putting a 1 in place of t. So if I take the 2015 population, N0, and I multiply by 1.07, I'm going to end up getting the 2016 population. I'd be, I guess, a little nervous about us potentially choosing option D. If you're too careless when you adjust 7% to a decimal, you might quickly try to choose option D. Hopefully it makes sense why the correct option is option C. So this one doesn't really have any context to it, but it is definitely the same format. Just looking at the answer options kind of implies that. We have a number, we have another number raised to a power. The power involves the exponent. So it definitely does fit the format of the function that we've been talking about over the course of this video. Now if you look at this one, it says the function q is going to have its value decrease by 45% every time x increases by 1. So every time x increases by 1, q decreases by 45%. So every time 1 year goes by, the value of the population decreases by 45%, if you want to try to think of it with some context behind it. Now they're telling us q of 0 is equal to 14. Which of these equations defines q? Now you have to make sense of this q of 0 information. If q of 0 equals 14, that is at time 0, right? At time 0, 0 years after this population is being monitored, we have an initial population of 14. That is N0. So if we recognize that, we can quickly narrow it down to either option C or option D. And if you pay attention to the phrasing, we are decreasing by 45%. So I would have 1 minus the decimal representing 45% in that set of parentheses, leaving us with option C. If you don't know how to make sense out of decreasing rather than increasing, you might go with option D, but because this is a decrease and we need to subtract off that rate of decrease, we're going to end up with option C. So here's the problem I was referencing earlier about the coupons. It says the given function models the number of coupons a company sent to their customers at the end of each year. T represents the number of years since the end of 1998. Time is only going to be measured from 0 to 5, so I guess from 1998 to 2003. And then y of t is graphed in the ty plane, so we have the t-axis rather than the x-axis. And then on the y-axis, we're going to have the number of coupons, right? That's what this function does, determines how many coupons the company passed out. What is the best interpretation of the y-intercept of the graph within this context? Now, if you think about this function, which is already built for us, we have 8,000 as the initial amount of coupons being distributed. Because this is smaller than 1, we can hopefully realize that they're going to decrease the number of coupons that they're going to pass out yearly, right? We had 1 minus something here rather than 1 plus, and then we're raising that to the t power. How do we make sense out of the y-intercept? Well, if you think about the y-intercept is when time is 0. So when time is 0, what do we get for the value of the function? Well, what we get is 0.65 to the 0, which is 1, times 8,000, leaving us with 8,000. We get the initial number of coupons that this company set from the beginning of the time frame at which this function was being used to model the number of coupons being sent. The initial year when they started monitoring this was 1998. If you look at these options, I think option D seems like it's pretty good. The estimated number of coupons the company sent to their customers at the end of 1998 was 8,000. Yeah, 1998's times 0. 8,000 is the value that we get there. So it seems like option D is correct. The y-intercept is definitely not 1428, so we wouldn't choose that. Minimum estimated number of coupons from the company sent to their customers during the 5 years was 8,000. No, this isn't going to be the total amount over 5 years. This is going to be the total amount at the end of 1998. Last question in this video. Bacteria growing in a liquid growth medium. We have 300,000 cells per milliliter during the initial observation. Number of cells per milliliter doubles every 3 hours. How many cells per milliliter will there be 15 hours after the initial observation? So I do want to build my equation here. I'm going to go with a similar strategy as we've used throughout the video. What is my growth rate? Well, if I am doubling every 3 hours, I have 100% growth every 3 hours, right? If I have initially 300,000, after 3 hours, I'm going to have 600,000. That's 100% growth every 3 hours. Now, we're asked a question about how many cells per milliliter there will be after 15 hours. So there will be 5 doubling periods in 15 hours if each doubling period is taking 3 hours, right? 15 divided by 3, I'm going to have doubled 5 times. Now, I built the equation that we've been using throughout this video, had the initial observation number, 300,000 cells per milliliter. 1 plus the 100% growth rate. And notice how I adjusted. I did not put a 15 here. I put a 5 there. So my time is being measured in doubling periods whenever I have a situation like this. And I have 5 doubling periods occur from the initial observation to 15 hours later. So I talked a little bit earlier about sometimes needing to adjust this t value from maybe years to days to months. In this case, we're adjusting it to doubling periods. How many doubling periods go by over the course of 15 hours? 5 of them. So if I take 300,000 times, this is 2 to the 5th power, what I'll end up with is I'll end up with 9,600,000. Now, there is a simpler way to do this. If you recognize that 5 doubling periods are going to go by, you can just take 300,000 and you can multiply it by 2. You can double it 5 times. The nice thing about this equation, and this should hopefully make sense as we close out this video, check out what this equation really is it's 300,000. This is really a 2 raised to the 5th power. So this is 300,000 times 2, 5 times. So hopefully that'll help you if you encounter anything similar as you're getting ready for your SAT.